Okie dokie, there's 13. We've got y equals ln of 3x squared. We want to differentiate that and evaluate the derivative at the value, input value x equals 5. Here's our table that will derivatives we need that I put down. We've also got properties of logs I've put down as well. Remember, times, you add the logs. So ln AB, a times b, you add ln A plus ln B. Divide, you minus, top, date, bottom. Yeah? And the power rule. A simple object to a power. That simple object to a power, this chappie can come down to ground level, so to speak, to be b log a, and then you've got ln1 is 0, of course. That little property there. So with that in mind, then let's do this differentiation. Here we can see that this isn't on our table. We need to make this look like something akin to what this, a combination, something like that. And we've got to use our rules, haven't we, to modify it so that it looks like something that we can differentiate on our list. Now we've got 3 times x squared. Now at first glance you might think, oh, I can use this power rule because the 2 can jump down to be here. But the trouble is, this rule here, and this is one of the most common mistakes, is this object is a single object to a power. This isn't a single object to a power, is it? Because there's a 3 in the way. So as so to speak, you can think, oh, I'll move the 2 down. Oh, hang on. It's going to hit into the 3 that it's times by. I can't move it down without getting rid of the 3. So to unwrap this then, because that's really what we need to do, we need to probably work from the outside in, so to speak. So we're going to work from the outside. We've got 3 times x squared. So the first rule to apply would be the times rule, wouldn't it? Times you add. So I can simply write this as y equals times you add. So first term plus the second term. And I can view the x squared as a single object. This is an object, that's an object, times you add. There we go. Now, the point of doing that is we've unwrapped that problem, and now this second part here, we have got a single term to a power. So we can invoke this rule then, can't we? And swing the 2 down to ground level. So we can now write y equals ln 3 plus the 2 comes down to ground level, and it's 2 lots of ln x. There we go. That's tidied up. Now we can differentiate. So let's do the derivative then, here. Because everything is on ground level, and everything fits into our table. So ln3, if you tap that in a calculator, what do you get? You get a number. So log n3 is a constant. Here it is. Any constant, no matter how flash it looks, differentiates to 0. So put that down. Plus 2 lots of log x, that goes to 1 over x. There we go. Now we need to tidy it up then. Dy dx is 2 over x. 2 lots of 1 over x is 2 over x. There we go. There's our derivative. Now we use the input value at x equals 5 then. Dy dx equals, just write 2 over x, of course. Wherever you see an x, overwrite it with the value that it has, which is 5. And then you end up with 2/5 or 0.4. That's fine. There's the answer then. That's 13 done. Little problem. Very common to make a mistake here when you're starting these things up, because you think, oh, I'll just swing that down, use the power rule, and just bring it down there. Trouble is, it's going to hit into the 3. It cannot do it. It's only if it's a simple thing to a power. See it? So we had to then remove the 3 by doing times on this rule here. So we could do times is plus the first plus the second, so it's ln3 plus ln x squared. And then we could use the rule. There's the 2 comes down to ground level there. Now we've got everything tidied up, all on our table. We can do simple differentiation, tidy it up, input the value, and obtain the derivative at that value, 2/5. Okie dokie, that's 13 done. Great.